a good image about, I'm just trying to think of a waveform view or graphical view of 8B, 10B that sort of helps illustrate.
No, I don't have a good view of 8B, 10B. I was going to try and show it with my hands. By the way, we are live.
Hey.
And but if you have something that shows baseline drift or something, that'd be excellent.
Well, I just quickly found something on Google Images that shows if there's big long strings, so I could probably share.
Yes,
So
that's exactly what.
Let me move this to another one. I'll send you the link to the image so you can bring it up. I'm gonna post it in the Discord. So I just threw a link in the Discord. You can see it in the Discord.
Got it.
Hey everyone.
Yeah, hey everyone. I'm busy trying to update Facebook real quick, and then we can start talking for real. Where's the stupid button that says share to newsfeed?
I'm going to do a quick post as well. So it says live now. That's awesome.
Yeah, we are live.
I'm going to do a share. I could hear ourselves too.
Hello, YouTube. Hello. Hey, I've been posting to Facebook. Maybe some Facebook people come join us today.
Hey, so we've got some interesting things in store today, Bill.
Yes, we do.
You promised me last week that we could, so I've just posted to LinkedIn there too. Some interesting stuff came up in the Discord about serializing and high-speed interfaces where you need a lot of data transfer, so we can talk about that. You've got the TDR showing now, so you've got a camera on the TDR, so that's cool. Because some weeks ago, Oshpark helped us out with giving us some 6-layer transmission line samples that you designed.
Yes.
So why don't we start there?
Yeah, I was going to say, using the Altium calculation for impedance, because I'm lazy these days. Did you use to hand calculate your impedance, or did you always rely on a CAD tool?
I've pretty much always used CAD tools. There were times I wanted to see if the CAD tool was accurate, so I would compare its results to a hand calculation. Right. But the only formula I had at the time, I'm thinking back at least 10 years, was the one in IPC 2221, I think is the IPC designer standard that talks about impedance calculation. It's a very generic formula that's not particularly accurate up above a gigahertz.
That was IPC what?
2221, I think, was the standard.
Okay.
If you ever do a CID training class, it's the impedance calculation formula they give you in that class. But generally, if you go look at the real Bible of impedance, which is the Transmission Line Design Handbook by Waddell, Brian Waddell, I think. Brian's his first name. So anyway, that one accounts for all the vagaries of fringing fields and things like that. You're dealing with a layered structure that is uneven and has non-homogeneous materials in it, right? So you've got glass and resin, and you have to account for that somehow, because wave fronts travel more quickly through the resin than they do through the glass.
Do they? I would have said the glass
has a much higher. So glass fibers have an epsilon, have a permittivity of around 9.8, much higher than, and the resin is very low, and the homogenized equivalent is what they say is, it's about 4.5. But at what frequency?
I would have said that the signal travels slower through the resin and was lossier than through the glass.
It's lossier in the resin, but faster.
And that's counterintuitive to me.
It's all to do with so epsilon or the permittivity is a measure of the material's ability to store charge in a dielectric.
Right.
Or, it's not necessarily any material, whatever the material is. It can have charge stored, and glass can store more charge in less space than resin, so it has a higher relative permittivity. There's more capacitance per.
Right. It's a better insulator, which is why I thought it would have been faster.
Yeah. So the high. I don't have it open right now. But the fastest a signal will travel is in vacuum, and that will be the speed of light, and it has. Vacuum or anything like a vacuum, like air is very much close to a vacuum, has a relative permittivity of 1 because it's multiplied against vacuum as the reference. So the higher the relative permittivity, the slower the signal speed, the wavefront speed in the material.
Okay.
But also the higher the capacitance for a given unit volume. Yeah.
Right. Right.
Yeah. So
and loss is where things get displaced in the dielectric, and so they actually physically move. Is that a good characterization?
Yeah. Think about charge. Okay, so it comes down to you can cheat a little bit and wave your hands and simplify it by using electrostatics principles. But if you think about it this way, it's more intuitive to me anyway. Like charges repel, and dislike charges attract. We all know that. So if you are stuffing electrons into a conductor on one side of a dielectric, all the electrons that are in the molecules inside the dielectric are repelled from those electrons and want to go away from them. And so, but they can't escape their bonds. The bonds are very strong, and that's what makes the dielectric a dielectric. They have such strong chemical bonds, or maybe it's a pure element like diamond. The bonds of the carbon atoms in the crystal lattice, where they're sharing electrons in that crystal lattice, and it's the electrons that are bonding them together in that crystal lattice. So talking about diamond, right? What makes diamond such a great insulator or dielectric is the strength of those subatomic bonds in that crystal lattice.
Right.
And so it's
electron sharing doesn't happen.
It's very hard to force any of the electrons out of there because there's such an equality between the protons and the electrons being shared in that crystal lattice that it's so perfectly balanced that it would take an immense amount of energy to force them to separate, which is dielectric breakdown. So if you have a ceramic capacitor, it has a dielectric that's very similar to what RF printed circuit boards might use. So it's very low loss, but it's a very strong dielectric with a very high permittivity and therefore very high capacitance per unit volume. And so they have layers of plates with this dielectric. Silica is a good example, or alumina is another one. And in a crystal form, that's ruby.
Right. Okay.
But as a sintered white
sapphire,
powder with,
Chris said, yeah,
with some kind of binder, which is usually an epoxy resin as well, it makes a great capacitor dielectric. So you were asking about loss, right? Because what you're getting at is loss tangent,
right?
And so what happens when you impose a charge on two plates separated by a dielectric? You're forcing the charges in the material in the dielectric to kind of repel from that or attract on the other plate. They'll repel on one side and attract on the other, but they won't break. So what happens is you're actually elongating or biasing the electron orbits in the molecules and the atoms in the dielectric. You're biasing all those electron orbits into an orientation, and that takes a certain amount of energy.
Right.
And that energy is where we get lost tangent from.
Loss. Heat,
because
basically.
As you're moving them into position, it's causing heat rise in the material.
Right.
And so some materials have a very high capacity and very low loss, and others have a low capacity and high loss. But the trade-off is propagation speed. So you have materials like Rogers, which are very expensive materials for RF PCBs, and they have a much higher dielectric constant. So the advantage of that is, for the same impedance, you have a much narrower trace. For the same thickness and same impedance, you can make the trace narrower because there's more capacitance in the material. So it can shrink the size of your objects on the board. But the other advantage, so it's a double whammy advantage. You get smaller shaped objects, but you also get less loss. Those materials have 10 times to 100 times less loss than regular FR4.
Right.
But
so, and somebody mentioned in terms of light, and this all obeys the same rules as light for
it's all electromagnetics.
I stopped myself there because you can go all the way down to actual electrons bumping into things. But when we're talking about wave propagation, it's EM propagation, and Planck's constant applies.
It does.
So,
yep.
So that's a great description, especially of loss, of how jiggling those, I hadn't thought of it in terms of just rotating orientation. I thought of it as bumping in the direction of travel, but you're absolutely right. It's more about orienting towards the opposite end of the trace on the other side of the dielectric. And again, and my son has learned the trick. Whenever I ask him, so now what happens when this and that? And he goes, it gets hotter. That's right. That's my famous question around the house. What's the coefficient of friction? It gets hotter, Dad. Leave me alone. It's so.
And that's
so,
intuitively, if you're a board level hardware designer, most of the time you can get by just knowing that, right? It gets hotter,
yeah.
But then if you're going to start doing something really high speed, or if you're going to do RF, and you're like, wow, I'm punching 50 ohms into AppCAD to calculate the trace width I need for a prototype made on 1.6 millimeter thick FR4, and it's nearly 3 millimeters wide. That's huge. How am I going to fit this? I can't do this. Well, then you've got to start realizing, well, that's why Oshpark offers 4 and 6 layer boards. So you make a 4-layer board, which has a very thin dielectric on the outer layers. And so the idea is the next 2 layers in are just unbroken ground planes, or ground and power. And then you can have a pretty good, fairly accurate 50 ohm trace that's not too wide.
Right.
So.
Right. Yeah, I should put Altium on this actual machine here, and then I'd be able to pull up the board design I did for this and the layers and whatnot. So quite simply, what this board is it's got, this one's not populated, but I ran a trace vertically, and then I ran one horizontally on the inside layers, and then for grins, I ran a horizontal trace on the outside. And so I haven't TDR'd the outside one.
Why horizontal and vertical, Bill?
So for, as you know, weave fabric, the weave, I'm going to put my good hand in front, has gaps in it. And depending on how there you go. So depending on, and I know you can give a better answer than I can on this, but the gaps in the fabric introduce discontinuities in those properties. And so they use techniques like smashing the glass so that there's no gaps in it, or using 2 layers of glass so that by the time they're laying on top of each other, you can't see through it except where my finger's missing. What would you add to that, though? What about that?
So printed circuit boards, generally FR4 or FR408 is a better quality version of FR4 that Oshpark uses, and many other fabs use it. It's a composite, right? So it's fiberglass matting with epoxy resin, and the epoxy has a very low dielectric constant and high loss tangent, and glass has a very high dielectric constant and low loss. But you put them together, you have this very complicated material where the electromagnetic wave travels through the glass slowly but with low loss, and quickly but with high loss. And you've got boundary interfaces in between them wherever you've got a piece of glass fiber, the edge of the glass is touching epoxy resin. That's a boundary.
Right.
And so if you want to get really in depth, you could even say there's going to be reflections and crosstalk all through the material. But the dimensions of those things are so small that the frequency range at which those happen is up towards light, infrared light and above. And that's why if you look at a piece of glass fiber, you can actually see it, because it's reflecting a bunch of light back at you at different angles because of the boundary conditions. Whereas if you if you look at a perfectly clean cup of water down into the water, if it's totally still and there's no ripples on the surface, it's almost like, if you look at it directly, there's almost no reflection. There is some.
Right.
But what's happening with visible light, with diffraction and reflection, happens at the entire electromagnetic spectrum. They're all electromagnetic propagation, right? So the same things happen with the energy as it's traveling through your circuit board material, but the frequencies we're dealing with are so much lower in electronics that we don't have to look at it that way. We can basically homogenize the whole PCB material and treat it all as one homogeneous mass. We're just now getting to data rates where we can't easily get away with that all the time. We have to have modified impedance formulas and propagation formulas that take some of that stuff into account, because it does affect the quality of our rising and falling edges on our waveforms, right?
Right.
So
go ahead.
No, I was just going to say, so Oshpark made this board for us, which is really kind of them. And they got it to you quickly, but you've actually put one together, and it looks like you're measuring it now.
Yes. And so what I've done is I've put it, let's see if I can hold it up without, no, I made the cable too short now. I can't extend it over into the frame of view. But what it is I have a good high quality cable going to the board from my TDR. This is a CSA 803 communication signal analyzer, who I got turned on to these by Leo Bodnar. You can see leobodnar.com. I think he even refurbs them.
Yep.
He repairs them.
Mike uses one too, right? Don't you, Mike?
Yeah, I think he went out and got one. And that's what happens. You see one of these and you have to have one. A guy from Hackaday went and bought the 1803, or the big brother of this, that has Ethernet, instead of just a picture tube.
Here's the thing. What would, just to preface why this is a good idea to use one of these CSA, the communication signal analyzer, what would a good TDR cost that has the same bandwidth as what we're looking at that you have there normally?
Wow. You know, I don't know, but if you were buying it new, I'd expect to pay tens of thousands, or have your company pay tens of thousands,
Right. They're not
like
cheap,
at least
right?
20. They're
Because
not.
it's one thing to build a circuit that will transmit bits that fast and receive them, and it'll work if you follow the right principles. It's
Right.
another to build a thing that can actually measure that and have such a much higher bandwidth and much faster input circuitry to capture the signal that you can actually zoom in and analyze it.
Right. Right. And right now, and I'll show this a little bit, I'm at 200 picoseconds per division on the
It's
screen,
crazy.
which
What a
means
thought.
5 divisions is a single nanosecond of the electricity traveling down a board.
That's cool.
So,
And I
and
see an inverted spike there, which I assume is a connector or something.
right. So what I've done is I've taken a good quality cable. It goes to the board, and then at the other end of the trace is a terminator. And what we see on the scope is, here's the scope, the impedance of the cable, right here. And
Okay.
so this is 50 ohms. This is a good quality cable. And then it hits the cable connector, and that's that big negative spike. And there's a little bit of oscillation. And then this is the impedance of the board, and you see it's within 5% of the cable. So that tells me that the math is pretty much correct that I used when I did this in Altium. And then it hits the terminator. Well, we see that the terminator isn't near as big a spike, so that tells me that the PC board and the connector are not a big discontinuity. They are some, but it's really the cable that caused the big spike. This soldered cable connector, it's not hand soldered, I'm sure, where it goes to the board is what's causing that first negative spike. Now, I happen to like that negative spike because that tells me without doubt where the cable ends and where my PC board starts.
Right. But the implication there is that connectors usually introduce some kind of discontinuity, particularly if
always.
they're lower cost.
Yeah.
And so if I'm designing an RF amplifier or a beacon that needs to go out a cable out to an antenna, I want the whole system to be 50 ohms because I don't want reflections or anything.
You don't want changes. Whatever impedance you're at, you once you're there, let's say you're at 30 or 70, you want to stay at 30 or 70. You know, you don't want to be changing impedances, which is where the reflection occurs.
Right. So just in case there's anyone watching this who's not familiar with time domain reflectometry, do you want to just give us a quick rundown of what even does this mean and what are we looking at there and how does it work?
Picture a tube of water, and you suddenly change the height of the water like a tsunami would, and you get that water change, that pulse traveling down that tube of water, hitting the back end and reflecting off of it and coming back. And so that's and we measure the time it took for the wave to come down and reflect. Time domain reflectometer. So you see it TDR, and honestly, even the switch, like the old hubs you had in your house, the switch you have in your house to do your own cabling, Ethernet, may have a built-in TDR function in it to tell you how long the cable is. And that's how we tell if there's a short in an Ethernet cable, or if it's a short, is it 2 feet away or is it 20 foot away? So we build TDRs in almost anything these days.
And we can do that because the materials used for dielectrics, used for the insulators in our transmission lines. So in this case, printed circuit board material, but it could be aerated foam inside a coax cable, right?
It could be nylon, it could be, yes.
Yeah, it slows down the
vacuum, nitrous oxide.
It slows down the propagation of the wave. So where in a vacuum, it travels at the speed of light, but in a cable, it's quite a bit less than that. And so if we know
with that ratio being called the velocity factor, it's comparison to the vacuum.
So what I always found tricky with TDRs when I was first exposed to it, we actually did it with oscilloscopes in a lab at college, analog oscilloscopes. That's how long ago it was, right? And we had huge rolls of coax cable and terminators and stuff, and we would have 75 ohm coax, and we'd have 50 ohm coax, and we'd have 50 and 75 ohm and dead short and open circuit terminators, and we would experiment with these things. But we'd send the pulse, and we'd look at the pulse on one trace. We'd have a dual channel oscilloscope. We'd send a pulse, and then we'd be measuring at the transmission end of the cables, and then we'd have a big roller cable and then an open circuit at the other end. And after a certain number of time divisions, the waveform, we'd have the pulse, and the waveform would step up again. And so what we're seeing is the original voltage level of our pulse generator, which is still sending a 1 or a plus 5 volts or whatever it was. But then sometime later, the reflection comes back up the line and the voltage adds.
Right.
So we're looking at a step wave, a stair-step waveform, but the bit we're sending is the first step, and the second step is the reflection superimposed over it. And so as you're going left to right across the TDR screen, what you're actually seeing is also a signal which is bouncing back. So it's traveling, you could think of it as traveling right to left back up the wire. It's going the opposite direction. And you have to keep that in your head somehow and mesh that with a causal time-based signal waveform that you're looking at on the screen. But you can do, you can use any oscilloscope as a TDR if you just set it up right.
You just need a pulse source that is in the frequency range that you're looking at to begin with. And so we measure those rise times, like for this pulse source, I'm going to imagine it's a 50 picosecond rise time. Is that true? You know, I've forgotten what the rise time is. Mike, if you know what the rise time is on an 803, let me know. So what I did was I'm abusing my TDR. I just took my terminator off, and here on the screen you see what we're talking about. Suddenly, after it travels down the cable, a whole bunch, all the voltage comes back because none got absorbed. Very little got absorbed. And then it's got to travel down again and comes back, and only a little more got absorbed. And it keeps, if you look at this, you'll see that a certain portion, until eventually it comes out to be twice the voltage that you sent, right? Is it twice?
So those are also other mini reflections on top of the reflections. Then there's a lot of back and forth,
all adding up,
and eventually it rises up. It asymptotes to basically the peak voltage of your. And this is something that really was difficult to understand. Also in college, was that when you're sending a signal from one chip to another on a PCB, that we used to do things like we didn't care about impedance on the traces on the board. If we're just doing normal logic circuits,
right,
you know, the one gate goes from 0 to 1, so it goes from essentially 0 volts output to 5 volts output, and that goes down the PCB trace to the other chip. And you could look at that on a scope, and if you're looking at a low enough bandwidth, all you see is the 0 to 1 transition, 0 volts to 5 volts. So why don't we see all that other stuff? And it's because there were actually reflections. It's just that they were so short in time interval.
Short between them, right?
Yeah, that you would. If you could zoom right in, we didn't have the technology back then, but you could do it. You could do it now, and we should probably set up a board to do this, right? So we can show it.
Right.
You can actually see the stair steps all asymptote up to the logic high level, and I remember what my digital electronics lecturer used to tell us was that we actually we deliberately use reflections to our advantage in basic low-speed logic circuits on a board. You do it without realizing it, but you're actually You're using them to your advantage to get to that
to the
high.
V out high. Yes.
Yeah, but if you have a poorly designed board and you're going faster with more modern logic families, then reflections become an issue, and you can actually look at those today and you see ringing, and the ringing is actually that impedance mismatch causing reflections, and that's exactly what you're showing there. Behind that connector, I'm seeing ringing. So it's all kind of the same thing and related, really.
So one of the things I did once I saw that ringing was I pulled this out, my little torque wrench.
Where do you get those? Eric Bogerson uses them, and they're really cool, but I couldn't see, where do you get them?
I've got two that I got off eBay. People make a 3D printed version of this, which I don't like. What they do is it wears down a nub each time, so it's the epitome of non-repeatable, right?
Oh, I don't
and the
like
whole
that.
reason why I would torque that connector down to a torque, and this is 5 pounds, I think, per square inch. Is that right, or is it newtons per whatever? But the whole reason I do it is just for consistency, and we've chosen 5. Some other connectors are 7, some are 3. So what you can do is every time you go down, and this will click when it gets to 5 pounds, and that way your connection is repeatable time after time. So yeah, I threw my torque wrench on there just to see if it would knock down some of that ringing. Look how clean it is after it hits the termination, though. I love that.
Yeah, it's nice when a thing comes together. I see that the impedance is a little bit higher on the board than it was in the cable.
But it's within 5%, and you know, that I use default Altium calculation, and I didn't do anything crazy. And so I'll take within 5%, as long as it's consistent.
Yeah,
if that jiggled around.
That calculation, by the way, is not based on the formula. From what I understand, it's based on a 2D field solver from Symbian software.
Right. So yeah, you were the first to tell me that.
Symbian makes a really good signal integrity tool. It's I don't know too much about it, but it's one of the ones out there that you'll hear about if you go to conferences and things that people talk about.
So what's Autodesk use for their calculation?
We use the calculation. It's up to the user, really. So the Eagle did not have impedance controlled routing in the layer stack up. That is something I am working to change. Hopefully this year if we can, but not in Eagle. In Fusion 360, we're investing in that right now.
Okay.
So and I can't give away too much or sell the future, but there's pretty cool things to look out for. In the meantime, I'm using Cook's Transcalc because Cook's Transcalc is free, and it's formula based, but it's actually the most accurate of all the formula based because it's using the data presented in Brian Waddell's transmission line handbook. So it's taking into consideration all the fringing fields and fringing effects, and it's the most accurate I've found so far.
All right.
It's even better than some field solvers because it's made from curve fitting a lot of empirical data on different board layups. So,
does it draw its genesis back to the IPC standard?
No, IPC draws its genesis back to the same research papers from the 1960s, but of course since then a lot more accurate work and updates have been done and new curves fitted to new transmission line structures in boards. And so Brian Waddell's book is good because it's the most modern. It contains that most sort of recent information, and so I would be using those.
What's the name of the calculator, the free calculator you said you use?
It's Cook's, the transmission line calculator in Cook's Transcalc.
Oh,
you can run it as a standalone. You can run
Transcalc was what you called it, yeah.
Yeah, but really it's just C++ implementation of the curve fitted formulas from Brian Waddell's transmission line handbook.
Right. So Mike posted what happens when you stick I don't know if you can see this. Can I click on it? Oh, there we go. That's what the output of the TDR looks like going into a scope. And actually you see a little Hey, Mike, can you try that again and set your scope for 50 ohm termination? Or is it already set for 50 ohm would be my question. But this is what the TDR looks like in the macro time domain.
Yeah, so all you need to do basic time domain reflectometry is a good square wave or pulse signal source, some good connections into the device under test, and the right kinds of terminations, and a fairly good high bandwidth oscilloscope will do the trick. And everything else, so here's a question for you for people who want to do it that way. And I noticed on the CSA that you're doing this too. You've got the y-axis or vertical divisions are millivolts. So how do you know what's impedance from that?
Well, I use the cable. That's my shortest answer. Is I know that cable's pretty close to 50 ohms. So I compare it to the cable, quite honestly, when I'm doing off the cuff stuff like this.
Yeah, so the cable's 50, and you adjust the volts per division so that the first pulse coming out of your signal generator is at 0, and then it goes to a logic 1, whatever that happens to be, and that might
happens to be, right?
That might be 100 millivolts in the CSA, right? So that 100 millivolts, where you see that go up and into your cable, that corresponds to 50 ohms, and everything there is proportional. So when you see a 100% reflection come back from the other end because it's unterminated,
right,
the signal voltage doubles. And so double the voltage means
unterminated,
open circuit. If the pulse went and then stayed at that, then we're looking at it's the same impedance. Or if it comes back and goes negative, we're dealing with a short circuit or lower impedance if it goes down.
Or active circuitry or something. So, yeah. You mentioned opens. This came with my VNA.
I can't see what you're doing there. You're still sharing the Discord.
Whoops. Yeah. Thank you. Yeah. Thank you. So this is my VNA. This came with my VNA, and it's for calibrating it, so there's a through, but it's got an official open and an official short position on it. Yep. Not that you couldn't make your own, but you might as well have a piece of calibration.
Yeah, I got little SMA connectors with termination and open and short for my USB VNA. And
right.
Before I use it each time, I let it warm up, because those high-speed A to D converters that they use.
Yep, my light will go green after about 10 minutes, telling me it's warmed up.
You want to let the whole thing warm up, so they stabilize temperature, and that's right. When you do your calibration pass with the open, the short, and the load, and then you start measuring. Yeah.
So ask me how I would make a TDR with an oscilloscope.
How would you make a TDR with an oscilloscope?
I would buy a pulse generator, and again, I got this from Leo Bodnar, leobodnar.com, and what I was doing was I was researching a pulse generator for a Hackaday article, and I started with avalanche diodes and pin diode. I looked at all these different ways. Mercury wetted relays can produce a pretty damn quick pulse, it turns out. But then Leo peed on my parade, so to speak, because he had already done it way better than I could.
So how does his circuit work? And is it open source? Can we look at the schematic?
No, it's, I imagine he would tell you, but what's in it is a laser driver. So it's meant to drive gigahertz lasers on and off differentially.
So, of course.
yeah, right. Because you can't build what's in a frickin' laser driver, you know? You can't build that out of discrete parts.
No.
And he went one further. he's got a USB port on it, and he's got a little app, and you can adjust something like the voltage maybe, and I forget what all's there.
So what's the SMA for versus the BNC connector? Which part of it's which? There's an SMA next to your USB port.
The SMA is a trigger output, and you need to know that so that your scope knows when the pulse occurred really. So what you would do is you would run the the trigger output to your scope and trigger your scope on it, and then the BNC connector is the pulse and the reflection and everything you would measure. So where would you measure that out? So you would put a T-junction here, for example, so you could see the pulse go by and then it return. So, and this is like 60 bucks USD, 60, 80. I don't want to, guess. My memory blows these days. It was under 100 bucks to do what I can't build myself without doing all this. So I love this. So you can get a scope and a pulse generator, and it's the bandwidth of your scope and the rise time of your pulse that will set how much acuity you have looking at these reflections. Now, what I was trying to do when I bought my CSA, and by the way, the way I learned about the CSA 803 is Leo sent a printout from his 803 showing me the rise time of the module I received. So real class act there.
So each module he characterizes and gives you the data.
He characterized
of your
it.
Module.
Yeah.
Why would you need that? That's cool, but why would you need it? Wouldn't they all be the same?
Yeah, I was going to say, for variations, and it's actually tunable. That's what the USB is for. You can tune it a little bit. I took it to mean that I knew what I was really looking at. I was going to accept whatever the pulse was.
Yeah.
The reason I looked this up and ended up on the CSA 803 is I wanted to show the effects of vias and square corners on a trace, because everybody goes, oh, don't use square corners. So I did a Hackaday article going, square corners don't matter unless you already know that.
Square corners only matter on impedance controlled.
Real high frequency impedance control.
You're doing microwave and millimeter wave.
That's right.
RF.
Then you need
boards. Then you want chamfered corners.
Right.
For optimum, impedance maintenance with no reflections at all. And
right.
the odd thing is, if you're talking digital electronics, we're talking very broad bandwidth signals, because you have a very high rise time pulse and then flat levels for some time. And with RF, you're dealing with a presumably sinusoidal carrier that may have something superimposed over it, or it's probably just a pure sinusoid that may be frequency modulated or something. But it's a sinusoid. And so if you have reflections on a sinusoid, it creates a lot of distortion. And that's the distortion that we're avoiding. Yeah. Yeah,
Mike just posted Leo's printout that he got with his CSA, with his Pulsar. So I guess Mike bought a Pulsar.
Yep.
So, hey, I have a question for you. Have you ever designed we talked about the properties of dielectric and its the effects on transmission lines, and we said the H word, heat. Have you ever designed for a self-heating for multi amps or anything that dealt with heat and TG of the PC board?
That deliberately heated it, or that had to get heat out of it?
So my theory is that in a big company, they have a department dedicated to SI, to signal integrity. And I always wondered, if you have a big enough that you've got a department for it, are your heat guys different than your signal propagation guys, or is it easy to wear both hats?
I think they would be different, because people who understand heat and heat flow usually have a mechanical engineering background, and they typically use different tools for simulating and analyzing heat issues. But there's, like all engineering of any hardware, there's always some overlap, and people collaborate and work together. So that's something I love about Fusion, and one of the reasons I went to Autodesk is because we've got computational fluid dynamics, we've got electronics assembly cooling. it's still kind of.
We could talk about cooling someday.
I could probably run a board through it, but the point is, we can see you can put heat generating loads assigned to different parts on the board, and say, like, this MOSFET here is dissipating 1 watt. What does that contribute to the overall heat?
Right.
And do we exceed temperature for our design? But FR4 is a very lousy conductor of heat, because generally anything that's good at conducting current will also conduct heat well, and vice versa. So if you want a good insulator, you're kind of out of luck with getting rid of heat, unless you do other clever things, like put a lot of copper vias through the board and attach a heat sink to the back, or do an aluminium backed board like the one you were showing me that you did for a front panel. The whole aluminium PCB is all about heat. So that's like a rigid flex. It's a polyimide substrate. It may be 2 layers of copper, or even 4, all done with polyimide instead of regular FR4, all attached by glue adhesive to aluminium, and the adhesive and even polyimide's lousy at conducting heat. So it's you get some heat through to the metal, but even then still it's better than nothing. But I still feel like the industry hasn't really come up with an ideal solution yet.
So what always goes through my mind when I talk about heat is like, well, how much current would you be pushing through a PC board? And in the old days, not a lot. I mean, we tended to do like big heavy loads as discrete wires. But nowadays, if you have a 100-watt processor, and it's running off 1 volt, how many amps is that?
That's 100 amps.
That's 100 amps.
That's
a lot. Yeah. That is huge.
And so this is why one of the hallmarks of PCB manufacturers advertising is now, oh, we can do 5 mil copper. Well, it's because how else do you get 100 amps under a BGA?
Right? How do you get it there? How do you get enough copper there, and then the board doesn't warp, right? Or the board doesn't crystallize from the heat, you know, and so one technique, I mean, we used it in the old days, board stiffeners that also doubled as power rails. So you would bus bars. So you would have a board with slots in it, mount this bus bar to the board, and it would hold the board rigid, but we'd also stick like, my stuff was small time stuff, but I could easily see somebody dumping 20 amps through one of those and not think anything of it.
Yeah.
So, yeah, I'll have to find a bus board. I did have an example of a bus bars on a board here, and it was for ferrite memory. The whole ferrite memory board had a couple bus bars holding the dang thing straight, just because the currents it took. Too. Yeah, they use tons of current, and they've got current sensitive components laying around in theory, right?
Yeah, talk about challenging design.
Yeah. Oh, read once memory. You know, when you read a ferrite memory, you destroyed it. So every memory cycle in ferrite memory was a read-write cycle. It was a read followed by a write cycle to restore whatever value you had gotten. So if you read a 1, you would write a 1 back to it, because after you read it, it's empty. You took the charge. So you can imagine how easy it is to propagate bit errors doing that.
The same, it's not exactly the same, of course. So I'm making a big stretch here, but even in DDR, like current generation or SDRAM technology, they have the same problem, because you've got a single MOSFET and a tiny little capacitance or a capacitor made with a single MOSFET as a memory cell for 1 bit. And by reading that, you're discharging it.
Yes.
And so they have this mechanism inside SDRAMs and DDR and DDR4, and you know, ever since SDRAM, they've had this mechanism for pre-charge. And that's what pre-charge does. It pre-charges, like it'll select a row of these cells, and it's kind of like a buffer with a feedback that that
kind of like a hold buffer, like we were talking earlier.
It's very similar to a bus hold, which we were talking about before we started. So I don't know if we're sort of 9 minutes to the hour here, but it's funny you brought that up, because it just looped it back to that whole thing. It's like lifting yourself up by the bootstraps. It's one of those sort of scenarios. But we use feedback, positive feedback in a good way, to, instead of creating oscillations, we're actually holding something at a fixed level quickly and easily. So you mentioned bus holds.
Well, actually, you reminded me when you talk about pre-charge on DRAMs, and I'm going back to the original DRAMs. We talked about access time, 200 nanoseconds or 120 nanoseconds, but that's not all there is to a DRAM. You have to let it rest for a certain amount of time for pre-charge to kick in. So we called it time row pre-charge, and so the cycle time was a combination of the access time plus the time it took for it to charge again. And that's what set the bandwidth in things like the old Commodore stuff. Wasn't just how fast was the DRAM, was how fast can you talk to the DRAM again, right? And so there's techniques.
Right.
So we had page mode, for example.
Exactly.
Where you get one row and then you go column, because you haven't had to recycle the whole row again. And the row driver is this big, huge thing, has lots of capacitance. So when RAS goes high and low, he's dumping and everything else. But once you do that, you can go column, and read out a couple, 4 to 256 columns in the same pre-charge cycle.
And that's what created cache. So we have
caching. That only works with good caching, unless magically the data you wanted is in the next 4 cycles or the next 256. So what they did then was they started having branch predictors and look-aheads, and they would go ahead and try and get those memory cycles. If you came to a branch and you would need this memory cycle if you took it, and this memory cycle or memory location if you took it, and this if you didn't, it'd go get both and put them in the cache for you. Or it would go and say, most of the time we take this, so we'll prefetch and it was called a branch predictor. And now it's just so frickin' fast. It's all, it looks like level 2 tightly coupled cache, most of the time these days.
So it's not so simple just to build an FPGA based design and say, well, I'm going to throw a DDR4 controller IP core in there, and then I can use DDR4. You can totally do that if you're running a 50 megahertz soft ARM core or something like that. That's just the pace at which the microcontroller core is pulling instructions or dealing with memory is a leisurely pace compared to what the memory can actually do. But if you want to do serious DSP or video processing, or something more like what you have in a laptop with a Core i7 processor, you have to start caching or doing things, or the whole system.
You need a DRAM arbitrator also.
It doesn't matter how fast your CPU is. It's never going to get. It's always going to be starved. The pipeline always gets starved without caching. So
you mentioned. FPGAs used as DSPs, what you can get a lot is, here's a process flow, and here I need some memory, and here I need some memory, and here I need some memory. And generally you won't have a DDR interface for each step along the way. You have to share a common pool of DDR memory. So how do you make it look like its own dedicated memory to all 3 sources, up to 7 typically on the IPs I've seen? And the answer is you need a DRAM arbitrator that goes, I'll get it for you. I'm already working. I'm already pre-charging. I'm doing this. Oh, you're number 3. Here's a byte for you. Oh, your priority's lower than his. I'm going to give him another one. Now you can have a byte. And so the thing acts like it's an arbiter. It acts like a funnel that makes one DRAM source, DDR source, look like 4 or 5 DDRs if you do it right.
Yep. And I used to design and work on FPGA soft systems that had a 32-bit RISC CPU based on MIPS-like.
Okay.
Altera has one. Altium used to have one when I was there years ago. I was supporting the FPGA side of the tools, so I would do these reference designs with it was called the TSK 3000. But we had a bus arbiter component. We would put that in there so the CPU could read and write and take its instructions from external SD-RAM. But then there was a video controller and it needed DMA. So DMA and MMUs all take care of this stuff, but they've all kind of merged into one kind of thing now.
They're layers of DRAM management.
That's what an MMU or
and
memory
virtualization
gives you. And if you want to run a high-level operating system that allows you to do multi-threading and multiple processes and run different applications, you need an MMU, and this is the reason why you're sharing one pool of memory with a bunch of different chunks of code.
Right.
And also different hardware, like the video output needs to, like you have a CPU that's doing a game animation. So it's got two memory buffers that are like, one is the current display and the arbiter is reading that out to your video output device.
Right.
The other buffer
emulates dual port RAM, only it does it through the front door.
Yeah. And the other buffer is, well, this is what I'm currently updating to change for the next frame. And so the CPU can be updating that one, and then there's the toggle that flips which one's being read out and which one's being written to. So,
Yeah. Now, we tried to use dual port DRAMs in the old days. They were such a good idea, and we never found a use for them. We tried so hard to go, oh, yeah, we'll just pipe the output. But too often these days, we're scaling the output. We're doing through memory non-linearly. And the dual port DRAM just never found its home for us. We would just double clock a DRAM from the front door and do, as you said, this byte for you, this byte for the display, this byte for you, this byte for the display. So
yeah.
What brand FPGA did you use when you worked in the old days?
Oh, I fooled around.
Because I'm going to slam one of the manufacturers here in a second.
Well, I messed around with all the big four. So Xilinx mainly, Altera secondarily to that, pretty frequently Altera, which is now Intel. Lattice, and I'm still messing around with Lattice devices, but I haven't finished my latest design.
They're cool.
Yet. That's
I like
another thing
Lattice.
we should look at someday. Lattice parts they've chosen to make very useful, very practical, and very affordable parts. And
they do 5-volt parts still.
Yeah, and they're really
with
awesome.
built-in memory.
Yep, and then
built-in flash.
To a far, far lesser extent, I was messing around with Actel ProASIC 3 and ProASIC Plus, and Actel somewhere actually kicking around. I've got an Actel Igloo Nano. Actel's advantage was they're flash based, so they were instant on, and they were inherently rad hardened. But I've never designed anything for aerospace, so it didn't matter to me. But they were super expensive parts. Right.
So now, I started on Xilinx in the old days on a CGA monitor, and you hand routed your Xilinx part. It had 64 blocks, 8x8, and it had like 3 different routes between each block that you could sit there and drop conductors with.
So you did your own
and stuff.
place and route and your own synthesis by hand.
You did, and half of us got out of that as fast as we could, and the other half got stuck doing it. And I'm like, why would you hand route? I know you did it just a year ago that way, but now you don't need to. Why would you? But so we use Xilinx, but I don't like Xilinx, and there's a reason.
Why?
And they lied to a friend of mine, and that's back in the Spartan days. I think the Spartan 1 family.
Oh, really?
When he went to run it at full speed, it didn't work. And if you look at like Lee Ritchie's books about bad BGA layout, I think they're showing Spartans. I think, you know, it just turned out they had to recall the whole frickin' line because it had too much inductance in its grounds. The ground would lift. All these things would happen. You could single step it fine, go at speed. It had problems. But the problem was they knew it, and they kept telling my friend, no, it's you. No, just keep using it. No, it was us. You want the Spartan 2 line. We're sorry we killed 6 months of your project. And that's what pissed me off. They should have told them, yes, we've got a problem. Hang in there and we'll fix it. We're communicating with you and we're being transparent and we'll do it. Then I'd still like Xilinx. But they hung my friend out to dry. Actually, an old Commodore friend of mine. And that's why I don't like Xilinx. Wasn't that they had a problem, but they didn't fess up to it when the guy was in the middle. And he was a user.
Yeah, and the thing, see, they do make, some of their products are really great.
So they are, and they haven't had a repeat, and they've. But
I get it. I get the frustration too, because what used to annoy me was they would announce a new family, and I was selling software for FPGA design and synthesis.
Okay.
And customers would say, "Do you guys support this Xilinx?" Like they would announce Spartan 6 a year before you could even buy anything, or at least 6 months before you could even buy a Spartan 6. And their top tier customers could get maybe engineering samples, but they'd be all over the electronics news about it with press releases here and there, and they were unobtainium. It was like vaporware.
And expensive. And yet,
I was trying to sell the software to help people design with them, and the people are going, well, we think we're going to have to use this new Xilinx family because it has the features we need for our product. And I'm like, and they're like, do you support that yet? Well, we can support it when we can actually get the parts and test our software. And Xilinx, can you get the parts yet? I would always say, can you get those? Do you have engineering samples? I'd really like to get a hold of them so our developers could, you know. And and it was so frustrating.
Right.
Like that.
Right.
So yeah, you know, I'm complaining about them too, but they could get away with it because they were the most popular and their products genuinely were the best in many ways. But today I'm using Lattice.
So I'm actually over at my cabinet, and I went to find a development board, and I don't see it there, but I was going to say for people wanting to learn FPGAs, again, I'm in the Altera camp. I just looked at the box my DE Nano came in. So Terra ASIC makes good development boards. They make excellent development boards. They actually list my company under the references, so I love them. And you can't get something oversimplified. Like I put a link in our channel earlier. Matter of fact, maybe I can show it.
All right.
So I got some of these from China. Yep. And so I just sell these through like herdware.com. And all I'm doing is making it so you don't have to wait a month for it to arrive from China, to be honest. But if you want, and this is nothing more than an FPGA with a clock and a couple buttons and a couple LEDs, mostly it's about the pinout connector, right? So that you can bring out as many pins as you want. And this is why I based like my Hackaday articles when I did Delta Sigma converters and R2R ladders and whatnot. But you can go to Terra ASIC, that's all one word, and get ones that they have built-in LCD, built-in DDR3s, built-in, so you can sit there and exercise those things without having to design one and blow the design, quite frankly, yourself. You can start on a working board and then migrate to your own board. Yeah,
that's something I do like about the FPGA vendors is generally almost all of them have a really affordable way of getting started. So we were talking about those bus hold things, but I think we might have to save those.
We're done for the day. Yes, we are. Hang on, just.
Hey, do us a favor if you're into Altera. I just want to quickly do a quick search here because one of our listeners developed a really good Altera-based board as well. That's Rob Sterling, and I'm just trying to remember the name of his. It's a Cyclone 4. What's his company name?
So while you're doing that, I'm going to answer a question out of the chat. Wes was asking me, he'd seen the picture of my finger torn off, and I said I was lucky to have the picture. What happened was, because I worked in trauma and had also had a history of medicine, they let me be my own trauma technician as working on my finger. So I got to act as my own technician, which took my mind off it. I kept a sense of humor. And then when we went and x-rayed it and we're laying my hand with this bone sticking out and the finger hanging on by a thread, the girl snapped a picture. She was so comfortable by me being comfortable in an emergency room environment that she forgot I was a patient. So we're giggling, we're laughing, going, this is really something. And we take a picture of it. Well, one of the other nurses sees her do that, and she got in trouble for the fact that I have a picture of my injured hand. And I had to offer to go down. I'm an ex-captain of a rescue squad and whatnot. I was willing to put on a uniform, come down and say, we're family. Don't put her in trouble because she treated me like family. I work at Cooper Trauma. You guys work at this other ER. We're all family. And she still got in a little trouble for taking the picture of me and sharing it with me. They're not supposed to do that. So the fact I even have a picture is kind of strange to begin with. So she emailed it to me and then got in trouble for it. So Wes, that's the story of why there's only one picture. I was lucky to have one. So I'm sorry, what were you saying?
No, it's okay. It doesn't matter. I was going to show a little Altera board that Rob Sterling designed. He had a company in South Africa called Deltronics, and one of the things he did was this Altera Cyclone 4, a simple board. And I think I have one around somewhere, so maybe I can.
Do you have the link?
No,
to his board, or did you not find it?
His site changed.
Okay.
I think he sold that business and started a new one since then. So, but yeah.
Yeah, we got people from Pakistan who I know through Facebook. We had trouble getting Facebook to cooperate with us. Ontario says hello. Do FPGAs on the fly, rerouting of portions? Yes. The question is, can you reconfigure an FPGA on the fly? And yes, there's IP made that allows it to rewrite itself based on what you're doing. So I can't even tell you to be careful. It just makes sense to reburn some of your FPGA on the fly if you're so inclined, but you have to know what you're doing.
Yeah, yeah.
And the part has to be willing to do that. It means portions of it can be rewritten from the other portions which are static. So it's not like you have to can dump the whole array. You have to dump just part of the array. So I forget what they call that. It's dynamic reprogrammability or something.
Yeah, dynamic reconfigurability. I think it's
reconfigure. Yeah. Dynamic reconfiguration. Yeah.
Yeah.
So wow, we did an entire hour with just a TDR. That's pretty good. We didn't get to any of the other things we had on deck.
All right. There's a lot to talk about when it comes to TDRs and signal integrity, I guess. So
yep.
Yeah, thanks for joining us, everyone. And I think I've got people waiting for me on meetings probably by now.
Yeah, we're over by 10 minutes now. So, well, thank you everybody for joining us. We'll be here again next week. We obviously figured out how to actually make the show happen every week on time. That's not trivial. And we'll see you here again in a week.
Yep. Cool. Thanks,
Join
Bill.
us on Discord. Yep, go to Coriolis-effect.com. There's a Discord invite there. Matter of fact, I think I saw Sophie on the list here from Hackaday. So
awesome.
Thanks, everybody. We'll catch you next week.
Yep.
Bye, Ben.
Bye. See you, Bill.